Okay, in this example, we're given an integral, so the integral over r of 4 times x plus y, all times e to the x minus y. We're integrating that with respect to area. And then we're given a substitution in this case. So we're given a suggestion of the substitution: x is 1/2 u plus v, y is 1/2 u minus v, and then r is the triangular region between 0, 0, -1, 1, and 1, 1. So let's just draw r quick. So we've got this region here is r. Then we have these different values up here of x and y. So x is 1/2 u plus v, y is 1/2 u minus v. So one of the things we need to do is we need to try and figure out what are these different curves in this region of r with respect to u and v. So let's try and take a look at that. So first let's try and see, well, what are they in terms of x's and y's? Well, this top line, this is, remember, 1, 1, and this is -1, 1. So this is the line y equals 1. So let's think about that curve. Well, if y equals 1, from our substitution, that would mean that 1/2 u minus v equals 1. Or that u minus v equals 2, or that u is 2 plus v. So that curve, that top boundary, is really 2 plus v. U equals 2 plus v. Now let's try and do the same with the other one. So taking a look at our region, let's look at this line between the origin and 1, 1. Well, if we find the equation of that line, that's the line y equals x. And while we're at it, let's just look at that this is the line y equals -x. So let's look at y equals x and see what u and v are going to look like there. So if y equals x, well, then that's going to mean that 1/2 u minus v equals 1/2 u plus v. Or canceling out those 1/2s, we'll have u minus v equals u plus v. We can subtract the u's from both sides to just end up with -v equals v, or that 2v equals 0, so then v equals 0. So we've got so far u is 2 minus v, and v is 0. And then if we look at y equals -x, well, that's going to look like 1/2 u minus v equals -1/2 u plus v. So then we'll have u minus v, if we cancel the 1/2s, u minus v is -u plus v, or that u minus v equals -u minus v. So we can cancel the negative v's and end up with u is -u, or add those over to get 2u equals 0, or then just u equals 0. So let's try and draw this then in the UV plane. Remember, r up here was in the XY plane. Let's draw the UV plane. So my new region S, in the UV plane, well, we've got u equals 0, which is the v-axis. We've got v equals 0, which is the u-axis. And then we have u equals 2 plus v. The way I've done this, I put u on the horizontal axis. So we might take that u equals 2 plus v and solve it for v, since v is really my independent variable here. So we could do v equals u minus 2. So we would come down to a -2 on the v-axis, and then we'll have a slope of 1. So that would be this line here. So then in between those three curves would be this region. We very well could have left it as the other form too. There's no reason necessarily that I had to do a UV plane. We could have done a VU plane instead. That's fine, but just be consistent with whatever you do. There is a correct line, there's a correct graph depending on which direction you put that plane in. So for this particular one, it goes this way. So now what we can do is we can use this picture to find our bounds, where we're going to be finding bounds for the U's and the V's. So we might look at this as like a vertical region. So we might look at V bounds first, where then V goes from this bottom line to this top axis. So that bottom line is that U minus, U minus 2 line. And then the top axis is that V equals 0. And then we're looking at what are the bounds for U that goes between. So then U goes from 0 all the way over to this intercept, which is at 2. So U goes from 0 to 2. So now that we know what our bounds are, let's look for that Jacobian so that then we can make the change over to our new coordinate system. So when we're looking for that Jacobian, remember we need to use those X and Y formulas from up above. So let's see the Jacobian. We had that X was, I'm going to split it this time, so distribute the 1/2. So it was 1/2 U plus 1/2 V. And then Y was 1/2 U minus 1/2 V. So then my Jacobian of xy with respect to uv, we're going to have the determinant, we'll do the partial of x with respect to u, which is 1/2. And then the partial of x with respect to v, which is 1/2. Then the partial of y with respect to u is 1/2. And the partial of y with respect to v is -1/2. So then we have 1/2 times -1/2 is -1/4. And then we have minus 1/2 times 1/2, which is another 1/4. So we end up with -1/2. All right, we're almost ready to put things in our integral. Let's just do a little bit of side work first, so that we can see what we're going to plug in, because we know that we're going to have to plug in an x plus y and then an x minus y. So let's just figure out what those are in terms of u and v first. So x plus y is that 1/2 u plus 1/2 v is x, and then we would have plus 1/2 u minus 1/2 v for y. So the 1/2 v's cancel and the u's add up to just a u. And then x minus y is going to be 1/2 u plus 1/2 v. And then we'll have minus y, so it'll be -1/2 u plus 1/2 v. So now the u's cancel, so we're left with a v. So when we set up our integral now, we had the integral of r of 4 times x plus y e to the x minus y. That was dA. And now we're trying to make our switch to our u's and v's. So our bounds for v, just scroll up a smidge here, we can see, went from u minus 2 to 0. The bounds for u go from 0 to 2. We've got 4 times x plus y, which is going to be 4u. And then e to the x minus y, which is going to be e to the v. And then we multiply by the determinant of, the absolute value of our Jacobian, which was a -1/2. And we did this dv du. Okay, so what we're going to have then is we'll have the integral 0 to 2, the integral u minus 2 to 0, The absolute value of negative a half is positive a half, which times 4 then is just 2. So we've got 2u e to the v. So we've got dv du. So taking a look then, we've got the integral 0 to 2. We're going to have dv. 2u is just a coefficient, so we'll keep 2u, and then we'll end up with the integral of e to the v will just be e to the v. So I'll have e to the v from u minus 2 to 0 du. So this is the integral 0 to 2. We'll have 2u times e to the 0, which is 1, so just 2u. And then we'll have minus 2u times e to the u minus 2 du. All right, so for each of these integrals, we're going to take care of them in two different ways. The first one is just a simple power rule. So it's just going to end up being 2u squared over 2, so it'll just be u squared from 0 to 2. And then this second integral, notice that we've got a u times e to the u minus 2. So we've got a linear function of u and the exponent of e, and it's times u on the outside. So u substitution isn't going to work because we don't have that du factor. It's not going to simplify the multiplication. So instead, we're going to use by parts. Normally, we would use a u and a v by parts, but u's already taken, so let's maybe use a w. So we're going to have to identify w and dv. So w we want to simplify when we do the derivative because we're going to find dw. And v we need to be able to still integrate. So we want it to be kind of a most complicated part that we can still integrate. So let's let dv be the e term. So e to the u minus 2, and this will be du. So then v is the integral of e to the u minus 2 du. Notice we could do a little mental substitution there. So we could let u minus 2 equal, say, like a another letter that we haven't used yet. So u minus 2 could equal t or something like that, but then we would just end up with dt equals du. So we would just have a single, a 1 factor there. So this is just going to then be e to the u minus 2. Choosing dv to be e to the u minus 2 du leaves that w is 2u. Notice I put the negative out front, so I'll hang on to the negative for later. So then the w being 2u makes dw 2 du. So then our by parts, our normal formula is uv minus the integral of v du. So instead we'll have wv. So w is 2u times v is e to the u minus 2. And then we'll have minus the integral of v, which is e to the u minus 2 dw in this case, which is times 2 du. And the bounds are still there, so this is 0 to 2, and then this one also will be evaluated from 0 to 2. Almost there. So let's see what we've got now. So u squared evaluated at 2 is 4. Minus u squared evaluated at 0 is 0. We'll then have minus 2u e to the u minus 2 evaluated at 2. We'll have 2 times 2, which is 4. And then e to the u, so 2 minus 2, e to the 0 is 1. So just a 4 there. And then we'll subtract off, plugging in 0, which 2 times 0 is 0. So that will evaluate to a 0. And then we have minus. Again, that e to the u minus 2 when we integrate is going to stay the same, so we'll keep the 2 as well. So 2 e to the u minus 2 evaluated from 0 to 2. So then we've got 4 minus 4. We'll have negative, negative, so plus. We're going to have 2 e to the 2 minus 2, so e to the 0, so just 2. And then minus 2 times e to the 0 minus 2, so e to the negative 2. So my 4's cancel, and I'm left with 2 minus 2e to the negative 2. Lots of 2's in our final answer. So this was an example where our region wasn't necessarily super complicated in the beginning. If we scroll back up to look at it, we probably would have chosen to do a dx dy integral, kind of go from those two x curves and then let y be numeric bounds. But doing this substitution in this example very much simplified the integrand. Rather than having that x plus y times e to the x minus y, which would have been a very difficult integral to do, we ended up with just the integral of that 2u e to the v. And remember that we did have to incorporate that Jacobian factor in there, which even though we had to do it by parts, still was a fairly straightforward integral that we were able to finish out here.